another Xafly Keys, another Xa talk show. Let's see if I'm alive. I'm about to be alive. Actually, I think I am already. Good morning and welcome to another Xa talk show. And today's topic is. Let me update the topic. So Compline blog, today's topic, okay, let me update the date. Oh, actually, this is bad. Shh, I forgot to put on my headphone. Now that's better. So, today I'm going to talk about the several subjects. It's showing browser. I'm sorry I'm late. So today I'm going to talk about several possible topics. So I'm going to show you some math books. Yeah, some math topic. I'm going to show you some math books. And I'm going to, well, I installed Python Anaconda. That's such a stupid name. I installed that. And I'm going to show you context dependent semantics, a very interesting issue about language design. Hi, guys. Say hi. And I'm going to talk about maybe possibly complex numbers. And I'm going to show you EMAC-Lisp sitemap. How do you use EMAC-Lisp to generate sitemap? Then I'm going to maybe talk about Mandelbrot set, which is mathematics. Then I'm going to maybe show you game of life. All of these are very interesting. Game of life, for example, that's actually computational, kind of in the subject of computation, but both computation and mathematics. Um, and the consequences of a game of life, the theories, it's far-reaching. Actually, it shows you how deterministic systems is actually unpredictable. Now, are you guys familiar with that? Okay, let's switch to. Hey, break the loop. Good evening. Great to see you. Now, you says, if I want to learn math through college-style textbooks, is there any particular author or title you recommend? Yeah, I can show you. Oh, calculus. Yeah, I can show you. Calculus. For example, James Stewart. Nah, well, you can get that book, but it's very expensive. Calculus, it's like, that's tremendous bullshit. So, okay, I'm gonna talk about that. So let's start. Let's get started. So, okay, let me show you calculus books. So I'm going to hold on a second. Let me, you know, I'm still kind of learning the whole streaming thing, and it's kind of awkward that every time I show this window to see the comments, it's kind of awkward. So I'm hoping maybe there's some way. So I still need to figure that out. Something like that, maybe. No, that doesn't work because every time I have to click this window. But yeah, but I mean, it's awkward for people to see this. But anyway, so okay, let me show you. So if you just xali.info, okay, and you go to the math section, that's my math blogs. And on the panel, you can see several entries. And what you want is math textbooks. Okay, by the way, you can also go to whenever you see the, on the, hold on the, never mind. Yeah, so this is, yeah, so I'm sorry, I'm being repetitious. I'm trying to get over that. So xali.info, click on math, then Oh, then you will arrive at my math blog, which is my math blog. But there's a main entry. If you click the yellow box on the top left, so this is my all my stuff about math. Uh, but if you want calculus textbooks, you click on this over here. So here is several textbooks, free textbooks that I've collected and verified. By that I mean I've either read it or I've checked the author, or read part of it, to make sure that this is something, it's good. Let's say I approve. Okay, so and actually many of these actually I'm planning to read myself. Uh, some of the differential geometry, actually some of the okay. Anyway, so on this page, is free math textbooks, and they are mostly in PDF. Now the topics on this page, some of them are um, kind of elementary. So, for example, if you never by okay, so if you are if you are not a math major, most programmers are not. You are not math major. Then this you can read probability. If you can read, without just high school with high school. If you have a high school qualification. So probability, calculus, linear algebra. Okay, so the first three topics, the probability, calculus, linear algebra, any undergraduate, and I mean if you are a programmer, you have some extra time, it's good to learn all these three. Now all these three topics basically are the fundamental, the basics, like every for example, if you go to a college, university for 4 years, and if you want to major in math, then you get a degree, right? So the first 2 years are basically calculus and linear algebra and differential equations. Basically that four topics. So calculus usually they divide to calculus one, two, three, four. I mean, depending on the college, but basically the first 2 years, I mean, every college and every university they differ. Their curriculum differ a little bit. So, but basically, all these linear algebra, calculus, probability, you can read, and it's good for you. I mean, if you are a programmer and if you are interested, because for any hard sciences, if you want to go to physics or if you want to go to engineering, you know, mechanical engineering or chemistry, you essentially you all require calculus and some probability, and and linear algebra is very it's like essential. Okay, but anyway, all these so far, it's basically the first 2 years of for math major. Okay, so but after so if you are major in if you are a major in physics, chemistry, engineering, any of these hard science classes, then it is required to take all these linear algebra, calculus, probability, and usually they are covered in first 2 years of a university. Now, however, if you are a math major, your major is mathematics, then the third year and fourth year, typically you will start to study real analysis and complex analysis and abstract algebra, uh, and and possibly differential geometry, and also possibly topology. That's the subject. I mean, again, every college differs, but I was but topology, abstract algebra, and real analysis and complex analysis, they are typical. They are almost fundamental for a math major. If you are a math major in undergraduate college, university, 4 years. So basically, the 4 years of college for a math major is all these. Um, yeah, and I got some other books, some of them for me to read. Logic, for example, I'm very interested. They are quite advanced, typically. Uh, and algebraic geometry is also typically a very difficult topic. But anyway, now let me talk about this math subject. So recall I differentiated from the first 2 years of college and the last 2 years of college for math majors. So for hard sciences, or all the mechanical engineer, chemistry. If you want to be a chemist or physicist, you all have to take probability calculus, linear algebra, and sometimes statistics. Statistics and probability, they are different subjects, but they are often studied together. So usually you'll run into a book that cover introduction for both of them. Basically, yeah, even though they can be entirely separate. But anyway, so so that's first 2 years. But however, if you are a math major, now that differentiate mathematicians from the others, physicists, mechanical engineer, rocket scientists, those are one thing. Einstein, he's a physicist. Okay, let's go over there. Now mathematicians is over here. So if you are a math major beginning the third year of university, you need to take real analysis, as I mentioned before, complex analysis, abstract algebra, differential geometry, and topology. These are typical. And I don't have differential equations. Basically, you need to take differential equations before differential geometry. So these are typically covered in the third and fourth year for math majors, and basically for math majors only. I simplified a little bit. Of course, if you go into, if you keep studying physics, then if you study, say, Einstein's relativity, then you also need, complex analysis. You'll need this, especially differential geometry. It's like, you know, so after you got undergraduate degree, then you go for master's or PhD degree. Uh, and sometimes like the topics varies. I mean, once you have an undergraduate, then some people take this first or some that first, and or some people never studied this topic. It's kind of like that. But anyways, yeah, so if you are just a programmer, you never studied math and you want to get into it, so these are so I have like three calculus textbooks. Let me turn on JavaScript. Okay, I have it. So I have like three calculus textbooks. These are PDF you can download. I mean, they are all open source. I mean, they are all some sort of creative license or open source, so you can download. I just put on my website. So there are these three calculus books. I haven't decided, which one is better. Because I took calculus. I took calculus back in 1991, so it's been a while for me. Um, but calculus gets you started. After yeah, so anyway, so I have these three books. I'm not sure which one is better. So you might just read them and see. I mean, they are all kind of similar. They are all kind of similar. You can just like pick one, start with one, see which one you like. Some of them cover a little bit more topics than the others, and also what interests me. When I study math, let me mention that on Wikipedia there's huge amount. Okay, the amount of articles on mathematics for mathematicians, not the basic stuff. I'm talking about. Even for mathematicians, professional mathematicians, the quantity and quality on Wikipedia, you could say it surpasses, existing all existing literature, even in many cases, even for graduate stuff, not research though, not research level, but yeah. So what I'm saying is that when you study these things, for example, this one calculus book, and let's look at some topics. And if you see, when you are reading this book, and if there's something you don't understand, you can always go to Wikipedia. It's useful. However, if you never studied calculus before, then I recommend you start with a book. You don't want to just go to Wikipedia, because usually when you go to Wikipedia, their stuff is spread out, and they have ton of things. And like one article, like let's say integration, you know that's a basic topic. But anyway, in general, you go to a Wikipedia for a specific math subject, or term. Then part of it is basic, part of it is actually research level, but it's all under that title. So it's kind of, it's hard for you to sort it out. For example, if someone never studied programming before and he goes to Wikipedia, he'll get overwhelmed, like all the languages and the programming paradigms. You don't know where to begin. You cannot tell which one is actually, the programming, for beginners, which one is what, which one is programming philosophy, like idioms, and so on, or programming history, Unix history, like for example, ask your mom or dad, maybe they are not programmers, they go there, they don't know where to, they get confused. So similarly, it's like that for math. So yeah, this calculus, you can start that. And linear algebra is great for linear algebra is one of my favorite topic. Linear algebra and complex analysis. Actually, I can go on and talk a bit more about math, because it's one of the topic I'm really interested. But let's look at the comments. So hi guys, if you guys have a questions, just ask it. Anything, okay? I mean, that's a nature of talk show for now. Right now I don't have I don't have a set things to discuss or plan. So right now it's just like, if you anyone, when I say something, you have a question or comment or your own opinions, just say it. So let me read the question a bit. Thanks for links. Were you ever interested in physics? When I was younger, yeah, but not really. I don't know much about physics, not and particularly not today. I don't like physics. I don't like physicists. Like everything physics. Physics. Okay, there's applied physics, and there's theoretical physics. Uh, but basically, essentially, every physics is reliant on math. You gotta have the math, especially. I mean, okay, there's applied, well, physics. There is experimental physics, okay, and theoretical physics. Now, theoretical physics is all just math. All you do every day is math. But why do they differentiate from math? Why don't they just call it math? Because actually their main goal is actually to study physics, theoretical physics, cosmology, quantum stuff, the shape of the space, the shape of space. There's a book by that name, which is very good, by Jeff Weeks. Well, I can show you. But anyway, so in physics, basically every physics is just math. You are just actually doing math. So but actually, it's more than math, because when you study math, for example, like the topics I covered, like, okay, like what I mentioned before, the first 2 years you have probability, calculus, linear algebra. Okay, that's basically that these are the first 2 years. And also I forgot to mention, also there's a differential equations. Okay, that's the first 2 years of college for hard sciences. But why do I separate it? So what I'm saying is that the second 2 years, that becomes a real math. But what's the difference? The difference is that the first 2 years of math, what you are learning actual practical stuff like programming. You are actually you can think of it as like learning programming, where you actually code and get answers. It's all practical. You do something. You get answers. How do you calculate? Suppose you have a circle. What's the area? Okay, yeah, that's easy. Pi, R2, something like that. But what if you have a curve, irregular shape, like a swimming pool or something? You know exactly each point in the perimeter. How do you calculate the area? That you do by calculus. You're learning. You do that by calculus. Okay, that's all practical. How do you calculate the speed? The spaceship, your gravity, so on. It's all practical. However, when you get on, I mean, but that's not like real math. Okay, that's not real math. That's not mathematicians' math. Today, as far as today is concerned, because um, that's practical, for engineers, for for physicists. you know the real kind of math begin today's, what mathematicians study. I might, I call it real math. That's not a good name though, but I mean, what the mathematicians today study today is all, um, basically they are all they are studying, formalized math. You could say that formalized math. So it's set theory and logic. It's basically everything's got a foundation, logic based basis. So for example, let me give you an example. So calculus, after you had this, introduction, the first 2 years calculus, then you start to study real analysis. What is real analysis? Real analysis is actually just calculus. In fact, as far as I know, in Europe, they just call it, like, they don't have two different names. They just have one name, like analysis. So anyway, let me explain. So what's the difference between calculus and real analysis? Basically, you can think of calculus as the, beginner's analysis, beginner's real analysis. That's kind of. So the difference is that in real analysis, it's the subject matter is pretty much the same, but however, you start to study it in a mathematician's way. That is, you don't draw things, or you talk about speed, or area. Like, you don't have that anymore, almost. Instead of your subject is all abstract. Like, for example, let's click it. Let's see. Remember in calculus books, you can thumb through. They talk about how to calculate area, change of speed, derivatives, integral, which is related to area, and things like that. Like practical, every person can kind of sense, everyday life. It makes sense. But in real analysis, which is kind of the beginning, mathematician stuff, if you look at the topics, it's kind of, you don't, it's all, abstract. You see, they mentioned derivative here, the Riemann integral, the continuous functions. That's still very basic though. But anyway, so what I'm saying is that the subject matter is, it's basically the same as calculus. Okay, but however, the approach, the whole approach and terminology used is all different. It's not like practical oriented. So here they define derivatives. So you start to see. For example, there's a website called Math Overflow. This is like Stack Overflow, except it's for mathematicians. And if you, let me turn on the JavaScript. And let me magnify. Now let me look at the comments a bit. So for example, this website Math Overflow, this is like professional mathematicians talking about math, just like we programmers talking about programming stuff in Stack Overflow. Now in Math Overflow, if you look around, they are using mathematicians language. For example, this question: comparing the definitions of K-theory and K-homology for C algebras. If you never studied math, that's what the fuck is going on? And it's like that. So that those are math jargons. When is a map of topological spaces homotopy equivalent to an algebraic map? Yeah. So these are all math jargons. Let's read another one. Intersection of free affine submodules, comparison with vector spaces. Yeah. So you see this math jargon. So what do they mean? Like, what do they mean? You'll understand what they mean after you read this real analysis book. It's you see here the definition of basic properties. So it definition 4.11. It says, let I be an interval, let fi2r be a function, and so on. They started to give you this math talk, the way mathematicians talk. So the real analysis. Let's go back to the page. So real analysis is basically the real introduction of calculus, like mathematicians' version of calculus. And complex analysis, it's basically the same subject as real analysis, except that they don't deal with real numbers anymore. They deal with complex numbers, which is a extension of real numbers. And complex analysis is my favorite subject, and it's beautiful. Yeah, it's extremely beautiful. I'm gonna show you. I mean, I can go on and on. Maybe if you like to see it, let me know. I'll show you later. Okay, let me finish this. Also, okay, so let me continue with this. So real analysis, it's kind of a math continuation of calculus. For mathematicians. Complex analysis is like real analysis, except it covers the complex numbers, which is very important. And abstract algebra. Now, algebra is entirely different subject from calculus. Okay. Now, generally in math, classically, there are many ways to categorize different math subjects, but classically, you have three categorizations. You have analysis, which is the same as calculus, but we call it analysis. So analysis, then you have algebra, then you have geometry. So analysis, algebra, geometry. This is the classic, roughly categorization of math. I mean, there are so many others. Like this, where does logic go? Logic is also a big branch. Um, and there's discrete math. There is no one way to neatly categorize them all, just like there's no one way to categorize all programming paradigms. You have OOP, you have functional, but functional languages, they also do OOP, something like that. Then you have other languages, fourth logical languages. So there's no neat way to categorize them. But anyway, traditionally math is categorized into geometry, algebra, and analysis. Now, what is analysis? Remember, analysis is just calculus. So the subject analysis talks about the study is basically continuous functions and limit. For example, let me give you a very interesting example. So suppose you have a stick, okay? Suppose you have a stick. You cut it in half, okay? Then you cut it in half again. Then you cut it in half again. If you repeat forever, the question is, Are you going to have something left, or will it like just disappear? That's an interesting question. This is a root of calculus. Beginning like 3,000 years ago, also 2,000. In Greeks. Um, so the question is going to be something left? So philosophers studied it. So on, but that question can be answered by calculus. It became so that's kind of the things calculus study analysis. So anyway, back to the categorization of math. So you have analysis, algebra, and geometry. Um, and algebra is about structures. Yeah, algebra is about structures. Geometry is my favorite topic. So let me read the comments. Let's see. So yeah, physics. Now I'm too old to actually. I would be lucky if actually. There's math I want to study, like differential geometry. I want to get. Um, I want to really know the stuff, and also proof theory. I don't have it here, but on another page. Yeah, I mean, and there are some things I want to study. I wish to study before before it's too late. I give myself like 5 more years. These two mathematicians, they are they are the top differential geometers. They are my friend. They are my mentor. My good friend. And I help them do their website. Yeah, let me show you. So virtual. So you search for virtual math museum. So there it is, 3D virtual math museum. So you go there. Uh, so you have different topics. You have, for example, polyhedra. Now this is a topic like every programmer likes, because it's easy to understand and it's elegant. And you also call it recreational math because anyone can easily understand it. So let's go back. So you have polyhedra. Uh, and you have minimal surfaces. Minimal surfaces is spectacular. It's really beautiful. So these are minimal surfaces. Basically, what they are is that if you okay, here's the interesting thing. If you have a wire, like any like a paper clip, I mean, suppose it's very long paper clip, just a wire, a copper wire, and suppose it's connected, so you have a circular copper wire. Now you twist it in any way you want. You twist it to any shape. Now you dip that wire into a soap film. Then you pick it up. Then the soap film will, they'll cover, they'll fill it, in weird shape. Now that shape is called a minimal surface. Why? Because due to physics, I mean, why does it form a particular shape but not others? Because that's because of physics. But in turn, but from a math point of view, those surface has certain properties. It's called minimal surfaces. So all these you see here are minimal surfaces. The most famous one and the earliest one is this one, helicoid. Helicoid and catenoid. Let's see. So here's an animation showing how they transform. But anyway, yeah. So if you want to study this subject, minimal surfaces, actually you have to study differential geometry first. So you have to study calculus and analysis, basic analysis, then differential geometry. So I'm trying to understand, I'm trying to learn. I'm learning, minimal surfaces. Um, so yeah, so let's go back to, yeah, and then we have famous surface. For example, you have Mobius strip. Mobius strip is famous because it's a surface that has only one side. Now, now there's a lot of significance to these these. People ask, so what's the point? Okay, you got a strip that only has one side. What's the point? There's a significance. Let me talk about it. you know a Mobius surface, it's a two-dimensional surface. Yeah, so it's interesting, it's only one side. It has only one side. Now the point is, why is it significant? Because you see, a surface is only two-dimensional. Now we so if an ant or any insect crawling on a surface, it crawl in one direction, it'll come back, but on the other side. I mean, there's only one side. Like there's just one side of it. It's kind of curious. Now, however, we live in three-dimensional space. Our space is three-dimensional. Uh, Now, is it possible? If you have a rocket, you shoot it up straight. It just goes straight. No bending at all. Just go straight. Now, it is actually possible the rocket will come back to us, like from our back. Why? Because of Mobius strip. So that is the significance. Because the Mobius strip is only two-dimensional. I mean, it's a mathematical abstraction. I mean, these the pictures are just a visualization. But you have like equations, to represent it. So this is just one of the curious, interesting example. And it's only two-dimensional. In the same way, you have three-dimensional stuff and four-dimensional stuff and higher dimensions. The point is that in three-dimensional or other dimensions, you realize, you by equations, you realize that it is entirely possible. I mean, it's not just, yeah, I mean, it's mathematically proven. It's not just it's just like the Mobius strip, such that if you go straight line ahead, if you have a rocket, going straight, it'll come back, to the back of your head. And that's the shape of the space. Why does it come back even if you don't turn? Because that's just the shape of the space. In the same way, like on the Earth, if you go straight, you'll come back. Yeah, that's a similar idea. But the idea that here is more complicated because it will not only come back, but the universe will be inside out. Like it is kind of like that. Yeah, so that's an interesting thing about these interesting things about these surfaces, shape of space. You know, and this conformal map. That's also this is the subject of complex analysis. Let me show you an animation. So anyway, so it's very interesting, and I'm helping. I build this site. I'm helping the professors. Building this site. Uh, let's see what I want to say. Yeah. Okay. So nobody's got questions. Yeah. I learned math mostly, by myself. Well, I had 2 years in college. I finished, all the math they offer. Like I mentioned before, all the calculus, differential equations, and linear algebra, and probability, intro to probability and statistics. Basically, that's it. And most others I learned on my own. So Are you credited on any academic? No, no. Actually, my only credit is a dropout of middle school. uh, can a Mobius strip exist in real life? Yeah, you just take a paper and make it. Let's see. I mean, if that's what you mean, you have seen people make it, right? So I got a strip. Let's make it thinner. Oh no, no, it's I tear off the. Yeah. So I got kind of a strip. So if I wrap it just like that, then that's a normal like a bracelet. But now I like twist it. Then I glue these two together. Then I got a Mobius strip. Then if you take a pen, if you try to draw, you'll see that it's just one side. Actually, there are a lot YouTube videos about that. There are a lot. There's like YouTube for everything these days. So, I mean, if you want to study some math, yeah, actually, there's even calculus course on YouTube. Though I'm not sure how good are they, but I believe some of them are done by professors. Um, yeah, so you can watch. So I mean, okay, when you study math on YouTube, many of them are fun. Okay, Mobius strip, so you can watch them casually. But know that if you actually want to study math, I mean, if you really are interested to get to know math, you don't want to spend too much time on these casual things. Because when I was younger, I studied them, all these. There are lots of like uh, 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 so, math popularization books. I read lots of them, like uh, Martin Gardner's books. I read all of them basically. And but okay. So what I'm saying is that don't be like me. Okay. Anyway, just kidding. What I'm saying is that when I was younger, I'm very much into math. Okay, but I spent a lot of my time when younger. I studied lots of these um, like intro to math, kind of recreational math stuff, math puzzles, or these Mobius strip stuff. Like on YouTube, you'll see lots of it, lots of those kind of things. And I mean, like fun and dramatic, visual stuff. So what I'm saying is that if you want to actually get into the heart of math, what mathematicians actually do, you don't want to spend too much time on these kind of YouTube, fun things like oh beautiful, oh you want actually to deal with the those math jargons and equations, like the kind of things you'll see on Math Overflow, and also let me say math is kind of a black hole, and the only reward is just self satisfaction. Because they are smarter people than you, far, far more. Doesn't matter how good you are. There are far more smarter people who know more math than you. Always. Doesn't matter how good you are. And they where do you find them? They are washing dishes at restaurant. What I'm saying is that, okay, no, what I'm saying is that, yeah, math is like a black hole. You can forget eating. You can devote yourself into it. However, one of the sad things is that it doesn't bring you money. You can study math like every day, starting today. You are really smart. You are, and you study math full time for 4 years. Um, you won't get a job. There's no job for you. So it's in sharp contrast to being a programmer. If you program, you learn Python after 2 years. If you're pretty good, you get a job. Lots of money. That's not the same for math. So math is kind of just rewarding for you. You know, and if you are, I don't know how old are you guys. So maybe some of you are young. You think you are a hot shot. You think you are high IQ. you know, um, just remember there are a lot of people far more smarter than you, and they are not doing well. I mean, if math is such a subject that it can suck certain people in, and just in some sense wasted your life. You can study it for like 20 years and get nowhere. It's kind of like that. But why do people do that? Because there's immense beauty in mathematics. Like, as Bertrand Russell say, math is the how the way what's the way he say it? Does anyone know? Um, well, Terence, uh, yeah, let me answer this question. Actually, I need to answer other questions above, but let me just say, I'm not a professional mathematician, and my math is not that, at let's say, it's reasonable to say I have a degree in math, okay, like undergraduate. So you could say I have, let's say I have a master's degree, or just bachelor degree in math. If I don't have a degree, but I have something like equivalent. So Terence Tao, I wouldn't, yeah, I've seen his blogs, but that's typically that's not something I would understand. I mean, I can. Well, there's a lot of mathematicians. I mean, for example, I met this. Well, yeah, I mean, so yeah, for example, on G Plus, on Google Plus, Google killed it. Google, is closing down in April, I think. Google, that's when Google started Google Plus. That's about the year that Google became, starting to become evil from that day on. This is like 7, 8 years ago, Google Plus. But anyway, one of the best thing happened to me is that I met this mathematician, John Bayes. I don't know. Maybe you guys have heard of him. He's very popular. So let me look at my. I just retweeted one of his tweets today, actually. So this guy, John Carlos Bayes. Oh, oops, wrong click. This guy. So he's a great guy. He taught me a lot math. Okay, he's actually a physicist. He's a quantum physicist. Okay, but however, one of the things he do is that he teaches math on kind of on online casually. By that I mean he write blogs, always in an expository manner. Um, However, there's a distinguishing quality about his writing, different from others. For example, you've seen those YouTube, stuff, right? The YouTube, they are fun. They teach you some math, like that. But they are not real math. I mean, they don't really, these are so-called math popularizing videos or math popularizing books. Like on Amazon, you can find a lot. The story of E and so on. There's quite a few math popularizing books. Well, actually, what, I should show my website instead because yeah. So anyway, let me get back to what I'm saying. So anyway, so yeah. Um, So so John Bays, he when he teaches some math, he's teaching the real math. Okay, not. I mean, he always teach it in a very interesting way. So it's still beautiful. I like, for example, you can see, it's still beautiful. This is actually physics, I think, or sometimes he talk about physics and chemistry. But he has done a lot math. But anyway, the way he makes the topic very interesting. But however, he keep it as real math, not just explaining something that for the mathematician. So what I'm saying is that if you have an undergraduate math, background, then you read him, you actually learn, the real thing. Many of the very interesting stuff. He started to use Twitter about half a year or maybe a year ago because Google Plus died. But on Google Plus, his stuff is far more better because Twitter, the child limit makes it very difficult, and also pictures are small. But if you go to his Google Plus, let's see, what? So he's got a he doesn't post to Google Plus anymore though because Google Plus is closing down. That's too bad. But anyway, you can find his just search his name on Google Plus. You'll find his great posts. Let's see if I can find it. Yeah, Google Plus is really a sad story, and it's also a story where how Google became evil empire. But yeah, anyway, you'll find it. You'll find it. People, I'm following him, but I stopped using Google Plus, and also he also stopped using Google Plus because it's shutting down. In the beginning, there's lots of people. Then it's just kind of going downhill and downhill. Anyway, yeah, search for you also follow him on Twitter. Uh, his Google Plus stuff is far better than Twitter because on Twitter you just can't do much. Okay, let me get back to the comments. So let me see. Uh, so let me see. Multi-dimensional discussion reminds me of the book Flatland. Yeah, Flatland is a great book. Great. So you guys have seen it, yeah. I read that too. I actually read that book 3 times. Yeah, let me show my website. I read it 3 times during different years. First time is like 1993 or something. Then sometimes in 1999, 3 or 4 times. Then 5 years ago again, I think. There's also a Chinese version, by the way, if anyone from China is coming here. So this is the book. It's a great book, Flatline. And by the way, many mathematicians has written sequels. You can see I list them. Some of this here. Flatland introduction. Uh, so people has written Sphereland, and also Flatterland and Spaceland. Now, I don't know about the guy who wrote Sphereland. but the guy who wrote Flatland, I've read like half of it. It's pretty good, by Ian Stewart. And Roddy Rocker, I know that guy. We have I mean, well, many of the mathematicians I've emailed to, talked. Roddy Rocker is also very old now. He's 70s, I think. Uh, he wrote Spaceland. I never read Spaceland. Land. And but also remember what I said before. All these books, these are kind of math popularization. I mean, including Flatland. They are great. They introduce they introduce you to some math subjects, but they are not math. Okay, they are not the real thing. If you are really interested, you want to spend time in the real thing. Uh, like the textbooks I have it here. um, Differential geometry. So the Richard Palais guy, he's my friend from back in year 2000, back in 1999. I think that's the first time we met. He invited me to Japan, Tokyo, Japan, and to Taiwan, the university, to give a talk and stuff. So he taught me a lot. He's 70 something now. Yeah, so he's got a introduction to differential geometry, a modern course on curves and surfaces. So this is back in 2003, and this is written in Taiwan. Uh, I was with him. Actually, he invited me to go there to teach a course to graduate math students, and I'm there to teach the programming of visualization of geometry. As part of the project for a summer course. So anyway, Richard Palais is a very interesting guy, and actually I went to his house 2 years ago. Let's see. So he's now at UC Irvine. He's retired. I mean, he's retired long, for 10 years or something. Um, so let's see. Let's go to keyboard. Where do I find? Okay, keyboard guide. So here I went to Irvine. Uh, do I have a picture? I don't have a picture of him. In 2017, he gave me the Mac. He gave me this iMac. Yeah. And anyway, so he is married to a Chinese wife, who is also a mathematician, differential geometer, Julian Deng. So this is her book. Uh, I'm reading it. I haven't finished Chilean book. Yeah, and this is also in Taiwan. So this is written back in 2004. So anyway, differential geometries. So uh, my IQ score. Well, my SAT score back in 1991 is what is it? It's like, I forgot what's the number, but it's like 90s percentile. It's like within top 10%, and that got me to into Mensa actually, the Mensa group, because one of the qualification is that in the top 10 percentile, if you of your SAT score. Uh, yeah, but the Mensa is kind of silly, you know. So there's Mensa Club, yeah, but actually you have to pay yearly fee. And this is back in 1992 or 1993, and you know back then you don't have internet like, yeah, like today, so they have like a monthly club, like the Mensa club, local club newsletters. It's kind of silly, actually, yeah, and you have to pay membership fee. So I quit after a year. So that's kind of today. I talked for an hour, but originally I was gonna talk about, well, yeah, math. That's a good topic, but I was gonna talk about complex numbers, Mandelbrot set, game of life. It's very interesting. Uh, and also, oh yeah, Python context dependent semantics. That's this one. So this is a example of context dependent semantics in Python. So for example, in Python, you can do from AA import BB, okay, or you can say import CC. Now, if you look at this, let me magnify. If you look at this, you see both of them contains the line, the import something, you know. But however, the import something in these two lines actually have different meaning. In the first line, this import something, that something is a function. In the second line, the import something, that something is a module name. So here is an example where the same syntax, the exact same syntax, has different meaning. In other words, it's context dependent. Uh, well, that's another topic. I can talk about. I was going to go into. So, any questions today? Hi Norman. Hi Panther. Haven't seen you guys before. Uh, so type questions. Questions. So if no questions, I think that's it today. Oh, regular expressions. Are you not using them? You are a programmer, right? I have lots of tutorials on regular expression. I have one for Emacs. Let's say, okay, let's see. Regular expressions. Okay, I actually I have like maybe 10 pages about regular expression of different languages. More than 10 pages. But let me find. Um, you know, wait. Uh, so there's Emacs one. XML is not S expression. Back then when XML was like a craze, this is around 2000 to 2005. XML is a craze. Everyone wants to do XML. Like there's XML language, based programming language. There's XML database. Like the entire relational database is gonna be kicked out. Instead, they're gonna have a XML database, and also all the configuration files in Unix or Mac, they or Windows, they changed to the XML format. So that XML kind of died today, but one of the consequence, a relic of the XML craze, is that on the Mac, you can still see many config files are XML. That is from this era. There's a whole craze. Everything. Like the entire computing world is going to switch to XML. But back to my okay. Let me show. What do you want to talk about regular expressions? The basics. Uh, okay, the basics. Like, are you programming in Python or JavaScript? Okay, let me show you then. So okay, go to xali.info. So let's open up JavaScript. Let's open up Python. Uh, okay, JavaScript and Python, and let's open up Emacs. Okay, so for the basic introduction, let me talk about Emacs first. So if you just go to my Emacs tutorial, practical tutorial, then you have a regex tutorial here at the bottom in the find and replace box. Then on this page, I show you the basic Emacs command for, there's a query replace regex and list matching lines. There are like more than 10 commands, Emacs commands that uses regular expression. For example, if you want to list all matching lines, for example, on this page, I call it a command. Let me show you. So if I call the command, actually, list matching lines, then it's going to ask me to type something. Let's say I type Python. So it shows all lines containing Python, and I can just click it, and it'll jump to the location in the file of the current buffer. So there are lots of Emacs commands that uses regular expression. Like you have to give the regular expression as argument. And so this page is a introduction to the actual regular expression. Like what does it mean? What pattern? What character? What syntax matches what? So first of all, explain what's the difference between wildcard. Wildcards. You have asterisk. And question mark. When you when you list files in the command line, you can use that. Let's see. CD to web. CD to web directory. Let's say, okay, so I'm in this directory and I do ls. You can do ls star html, and that will list all files starting with any character and end with html. So that's called glob. In Unix jargon, that's a Unix jargon called glob. So that's very useful, and a star sign matches zero or any character, zero or more characters. A question mark just stands for any character, but the usefulness for pattern matching is very limited. So I give you some examples. So then I start to introduce you to regular expressions. And here is a list of the most commonly used regular expression patterns. So anyway, so this page I give an introduction to regular expression. Okay, so that's Emacs. Now, if you are now let's go to Python. Similar for Python. So in Python, you go down. Here is a regular expression basics. So this code is a simple use of a regular expression. For example, you have a file. That file contains many email addresses, and you want to list, all the email addresses. You can run this code. Just save this in a file and run it as an example. It'll just show all email patterns. So that's a very basic example of using regular expression. Then you have find and replace. You can learn. So this is an introduction to regular expression. And then you have another example of using regular expression to split lines. And then you have regular expression reference. Python rejects reference. Now let me talk. So regular expression is extremely useful. Okay, if you are a programmer, you want to be very familiar with it because it's super useful. Uh, but however, when I first learned the expression, regular expression, it's fairly complex. So the thing about regular expression is that you want to persist. Okay, you want to persist. Um, you know, start with the example like the Python example I have here. Maybe you code in Python, or maybe you code in JavaScript. Let me go to JavaScript. So this is my JavaScript tutorial, and you can see at the bottom the JavaScript basics. At the bottom is a regular expression basics. So it's so you can copy this in the console, in the browser console, and you can start to run it. Uh, you know, so that's a basic example, and here is another example of matching all email address patterns. So in a file, you can extract all email addresses. It's another basic example. So I give you some basic examples, but then okay, so in different languages, you have a function that tries to match strings or find and replace using regular expression. Now, regular expression itself has a particular syntax. For example, in Emacs, I've shown here are examples of common regular expression syntax in Emacs. And in Python, you want to go to the Python regex reference. Here is my documentation. I've wrote it, for the Python regular expression. So regular expression, it has a syntax. Okay, the syntax is, you can see here, regex pattern syntax. Okay, so this is a Python example, regex pattern syntax. Now let's go to the JavaScript. Now the JavaScript, on this intro page at the bottom, you will see also a page on regular expression syntax. And on this page, I explain, I give you the syntax, basically all the syntax for regular expression. Now, when you do just remember, when you learn expression, regular expression, it takes time. Okay, you cannot like understand the whole thing in 1 week. It takes many months, or maybe even a year or two. Constantly using it, you'll get used to. So just remember that it's kind of confusing at first. You just have to get used to. That's one thing. Okay, the other thing about regular expression syntax is that different language, they differ, slightly, a little bit, but basically they are all the same. Now, Emacs regular expression is kind of more different than Java or Python. But anyway, Python, Java, Perl, JavaScript, Ruby, Golang, all their regular expression is kind of almost 100% identical. So you don't really have to worry about, which one to learn. So, just learn the one, whichever language you are using. Just, um, so I only have one for, JavaScript and Python. But basically, they are all the same for any language. You know one, you know the other, except Emacs. The Emacs this the Emacs version of regular expression is slightly a bit more different. So you know it's, yeah. So I think that's it for today. So thank you, super, thanks. I'm glad. I'm glad I did. I can explain it. So I see you guys. Hello, hold on. One more question. Web standards are too complex. That's true. Exactly. Browsers almost impossible to build from scratch. Yeah, yeah. Will the web be replaced? Oh, the question: Will the web be replaced in a couple of decades? Nah, I don't know. It would be very hard because it's so much technology has been invested. The web. Like you are exactly right about the browsers. They are extremely complex. I mean, it's not like a same person. I mean, doesn't matter how good you are. You cannot write a web browser in 3 years. I mean, full time. Let's take whoever the greatest coder at Google. Whoever who Let's for example pick the greatest coder at Google. He cannot. You will not be able to write a browser for in 3 years. Uh, you know, well, he can. I mean, you will be able to, but your browser will not be comparable to any of the Google Chrome or Firefox. You know what they do? They put programmers like the top programmers, billions, millions of dollars to do all kind of possible hacks to make it fast. It's beyond just good quality code. Suppose I'm a genius, and suppose I'm a Superman, and suppose I know all the protocols, the computer science, or all the by heart. I write a browser. It'll be very slow. It'll be slower than Chrome or Firefox or Microsoft Edge. Because what the corporate, the Google, they what they do is they have to hack. They try all possible ways to hack. Use assembly language or many tricks. They like hack, that is, to make it fast. That's what happens today, and in fact that happens in lots of things. So it makes it impossible for average persons, a software programmer, to compete with any of these companies. I mean, that's just the state of the thing. So anyway, so web browsers, I don't think it'll be. I think I don't know if something will replace it. I think it'll be hard. Not in 5 years, maybe not even in 10 years. Oh, next couple of decades. Decades, yeah, maybe. Yeah, decades, definitely. Maybe after 10 years, yes. I'm pretty. Yeah, I'm pretty positive about. I'm pretty certain after 10 years something will happen that'll replace the web browsers. Yeah, I'm pretty sure. Like maybe virtual reality or something. That's my that's my guess. So anyway, thank you guys for coming by. That's it for today. Bye.